On the Giza Plateau, where the Sahara meets the sky, there is a mountain built by human hands. 6.5 million tons of limestone and granite, 2.3 million individual blocks, 481 feet of vertical stone that held the title of tallest structure on Earth for nearly 4,000 years. And here's the detail that ought to stop you cold. The foundation beneath all that weight covers 13 acres, and across that entire footprint, the bedrock was leveled to within 2.1 centimeters, less than the width of a thumb, across 2.5 football fields of desert stone. We were taught the story in school. Pharaoh Khufu, 20 to 27 years. Copper chisels, wooden sledges, rope, earthen ramps, and tens of thousands of workers under the Egyptian sun. The Wadi al-Jarf papyri describe the logistics. The relieving chambers bear red ink markings naming Khufu and his work gangs. The tools were simple. The organization was extraordinary. And for the bulk of the structure, that story holds. But in March of 2026, a research team did something no one had attempted at this scale. They didn't pick up a chisel. They didn't dig a trench. They built the entire pyramid inside a supercomputer. And they gave the simulation a set of rules drawn straight from the archaeological record. No iron tools, no wheeled heavy transport, no compound pulleys. Only what the Fourth Dynasty actually possessed: copper, rope, water, stone, and human muscle. Then they let the machine find its own way up. The framework merged 3 disciplines that rarely share a room: parametric geometry, discrete event logistics, finite element stress analysis. In plain terms, they taught a computer to think like a project manager, an engineer, and a stonemason all at once. And when the simulation finished its 10,000th Monte Carlo run, the result was not a confirmation of what textbooks already say. It was a construction method that, by the numbers, should not have worked as well as it did. To understand why, you have to start with the precision. Because the Great Pyramid is not merely big, it is exact in ways that size alone cannot explain. The base is leveled to roughly 0.009% deviation. That is 10 times flatter than the tolerance modern building codes demand for large foundations today. 10 times. Using laser levels and computerized survey equipment, we struggled to match what was achieved with water channels, wooden squares, and plumb bobs. The conventional explanation is elegant. Cut shallow trenches, flood them, let standing water find its own plane under gravity, mark the line, drain, and cut to the mark. Beautiful in theory. But when the researchers modeled it at full scale, accounting for desert evaporation, wind ripples, and the accumulation of tiny transfer errors across 230 meters, the simulation kept returning the same answer. Possible? Yes. Probable? The probability curve said otherwise. The water method should have produced centimeters of drift. The pyramid shows 2. Then there is the alignment. The 4 sides face true north, south, east, and west to within 3 arc minutes. An arc minute is 1/60th of a degree. At the scale of the base, that error is smaller than the width of the full moon sitting on the horizon. In 2000, Egyptologist Kate Spence proposed a brilliant solution. Track 2 stars, Mizar and Kochab, and when one sits directly above the other, the line between them points to true north. The method works. But the simulation asked a harder question. How do you transfer that celestial measurement down to a 13-acre stone platform without losing the precision in the handoff? The machine found that half a degree of error, 100 times larger than what exists, would have satisfied every religious and ceremonial purpose. No priest could have perceived the difference. No ritual required 3 arc minutes. And yet the builders achieved it anyway, on a structure where any shift during construction would have compromised everything above it. But the simulation's strangest findings came when it stopped admiring the finished product and started modeling how it got there. For over a century, archaeologists have argued about ramps. Straight ramps? Spiral ramps? Internal? External? The problem is always the same. The volume of material needed for a traditional external ramp would rival the pyramid itself. The logistics collapse under their own weight. The 2026 computational model proposed something different. An integrated edge ramp. A helical haul corridor formed not by adding material, but by temporarily omitting perimeter blocks, creating an open-air path that spiraled up the faces, then backfilling the gaps afterward. No external footprint, no mountain of rubble to remove. The computer tested it with real physics: friction coefficients, crew spacing, corner-turning delays, lock placement headways. It ran 10,000 simulations, varying every parameter that could go wrong. The results were startling. A single ramp would have taken nearly 50 years, but an adaptive strategy, shifting from 16 parallel edge ramps in the early courses down to one final helical path near the summit, completed the on-site assembly in roughly 13 to 16 years. Add quarrying, river transport from Tura and Aswan, and seasonal pauses, and the total timeline falls comfortably within the 20 to 27-year window written in the Wadi al-Jarf papyri, the oldest administrative records from the construction itself. Even more surprising, the model's predicted ramp channels align with anomalies detected by the Scan Pyramids project. In 2023, muon radiography revealed a 9-meter corridor above the main entrance that no one had predicted. In April 2026, Scan Pyramids confirmed hidden voids behind the eastern face of the Menkaure pyramid, suggesting a second entrance. The computational model did not know these discoveries existed, but its predicted temporary channels, corner platforms, and backfill signatures fell within meters of where the muon detectors found empty space. The machine had not been fed those coordinates. It derived them from physics and logistics alone. And then there are the ratios, the ones that have fueled speculation for over a century. The perimeter divided by twice the height lands within 0.05% of pi. The apothem over half the base approaches phi, the golden ratio, to within 3 decimal places. The conventional explanation has always been practical. The Egyptians used a sect, a slope ratio of 14 to 11, which naturally produces pi-like relationships as a byproduct of the measuring wheel. The simulation confirmed this. A sect of 5.5 palms, chosen for stability and aesthetics, mathematically bakes in both ratios without the builder ever needing to know what pi or phi are. But the simulation also revealed something the textbooks rarely emphasize. The sect was not the only option. The Egyptians could have chosen steeper or shallower slopes. They chose this one, and in choosing it, they encoded mathematical relationships they would not name for another 2,000 years. Coincidence? The statistics say almost certainly. But a coincidence that required a specific choice at the foundation, a choice that determined every block above it. So where does this leave us? The computational model did not find aliens. It did not find Atlantis. It found something harder to dismiss. An engineering culture so sophisticated that its simplest practical decisions produced results we still struggle to replicate. The integrated edge ramp is not a fantasy. It is a falsifiable prediction. The researchers published every parameter, every equation, every line of code. They named 6 specific tests, from ground-penetrating radar to petrographic analysis of corner blocks, that could prove them wrong. That is the opposite of a mystery. That is science. But the simulation also left one question unanswered. The granite beams above the king's chamber weigh up to 80 tons each. They span more than 5 meters and have not sagged in 4,500 years. The model can explain how they were lifted. It can explain the ramps, the counterweights, the rope roll stations. What it cannot fully explain is the mind that looked at a quarry 500 miles away in Aswan and said, "We will bring that here, lift it 200 feet into the air, and set it so precisely that the seams are still holding today." That part remains human, and perhaps that is the real revelation. Not that the pyramid is impossible, but that we have spent centuries underestimating what is possible when intelligence meets patience at scale. So I'll leave you with the same question the simulation left its creators. If the Great Pyramid is merely a tomb built by Copper Age craftsmen with rope and wood, then which detail surprises you most? The 2-centimeter level across 13 acres? The 13-year construction window the computer had to invent to make the math work? Or the fact that a machine, given only ancient constraints, found a method we never imagined? Tell me in the comments which one you can't look away from. I read every reply. And if you want to see what happens when we point this same model at the Sphinx, you already know what to do.